In this video, we're going to look at some examples of solving triangles with the law of sines. In this first example, we want to solve the triangle where angle C is 140 degrees, side length B is 1, and side length C is 9. Since we know an angle, in this case angle C, and the opposite side, this indicates that the law of sines is a good tool to use in order to solve this triangle. We'll start by letting sine of C over C equaling the sine of B over B. We'll use this particular version of the law of sines because we know information about angle in side C and side B. We can substitute in our unknown values, and we get sine of 140 degrees divided by 9, and that will equal the sine of angle B divided by 1, side length B. And therefore, we see that the sine of B is going to be the sine of 140 degrees, all divided by 9. And according to a calculator, this is approximately 0.0714. The sine of B is this number. And so we can try to find angle B by taking the inverse sine of this value. So the inverse sine of 0.0714. And this is approximately 4.094 degrees. So this is the first value for angle B, 4.094 degrees. Now, if you do get a different number here other than 4.094, double check to make sure that your calculator is in degree mode. If your calculator is in radian mode, it'll give this angle in radians, but we want the angle in degrees, so make sure the calculator is in degree mode. Right. There's always a second possible triangle using the law of sines. So I'll write this as B2 as the possible angle here. And this angle will always be 180 degrees minus this first angle, so 4.094 degrees. And this would be 175.906 degrees. This is always the potential angle that we need to check, but we have to determine whether or not it will be a solution. Now notice here that we already have an angle that's 140 degrees, and if this second angle were indeed an angle in our triangle, we would have the angle sum being well over 180 degrees. Those two added together will certainly be greater than 180 degrees plus a third angle in our triangle. And so that tells us that this second value of B will not be a solution in this particular example. So we only have one value of B here, and that is 4.094 degrees. Once we know two of the angles, which we now do on B and C, we can subtract the two known angles from 180 degrees to obtain the third. And so here we obtain A to be 35.906 degrees. This is our angle A. We now know all three angles of our triangle. The last piece of information that we need to find is angle A. Side length A. To find side length A, we're going to use the law of sines again, this time involving the values for A. And we can again use the sine of C over C since we knew we were given both of those values. So here we have that the sine of 35.906 degrees divided by side length A will equal sine of 140 degrees divided by 9. We can solve this equation for A, and we see that A is going to be 9 times the sine of 35.906 degrees divided by the sine of 140 degrees. And using a calculator, this is approximately 8.211. And so this is our value for side length A, which is the last piece of the puzzle that we needed in order to solve this particular triangle. In this example, we want to solve the triangle where C is equal to 6, A is equal to 8, and angle C is equal to 35 degrees. Again, we're going to apply the law of sines because we know the angle C and side length C. And so we can use that the sine of 35 degrees, angle C, divided by the side length of C is going to equal the sine of angle A divided by the side length A, which is 8. From this, we can then solve for sine of A. Sine of A will be 8 times the sine of 35 degrees divided by 6. Using a calculator, we can see this is approximately 0.7648. This is the value of sine of angle A. And so when we solve for A, we can use the inverse sine function. And again, a calculator. So the inverse sine of 0.7648 will be approximately 49.89 degrees. And again, if you don't get this number, check to make sure your calculator is in degree mode. We always have to check the second angle here. It's always the angle in quadrant 2 with this same sine value. So that'll be 180 degrees minus 49.89 degrees. And this will be 130.11 degrees. So now, if we look at the two angles that we would have in this second case, 130.11 degrees plus the angle C, which is 35 degrees, this would be equal to 165.11 degrees. And unlike the previous example, this is less than 180 degrees. This means that this is actually a valid triangle, that this A2 will give a valid triangle along with the three pieces of given information. And since this angle, the sum of our given angle and angle A2 is less than 180, at this point we can conclude that we actually have two triangles that meet our initial data. There's one where angle A will be 49.89 degrees, and another where angle A will be 130.11 degrees. To find the rest of the information for each triangle, we'll look at these as two separate cases and proceed as in the previous example. For triangle 1, we're going to assume that angle A is 49.89 degrees. We already know angle C is 35 degrees, and so to find angle B, we can simply just subtract the two known angles from 180 degrees, which is the angle sum of a triangle. And we see that B in this triangle would be 95.11 degrees. Once we know angle B, the last piece of information we need is side length B, and so we can use the law of sines once again. We would have the sine of 95.11 degrees, sine of B, over the side length B, which is our unknown value. And this will equal the sine of angle C, which is 35 degrees, all over side length C, which is 6. From this, we see that B will be 6 times the sine of 95.11 degrees divided by the sine of 35 degrees. And according to a calculator, this is approximately 10.42. So this is our value of side B in triangle 1. I'll leave it to you to solve triangle 2, though the values are listed here. The steps are exactly as followed above in triangle 1, just with a different angle A, 130.11 degrees, as we saw previously. You can use the angle sum formula to find angle B, and then the law of sines to find side length B. In this example, we want to look at solving the triangle with B equal to 2, C equal to 1, and angle C equal to 50 degrees. This looks a lot like the previous examples we've seen, but as we'll notice, something weird does happen when we try to solve this particular triangle. In particular, we should start off using the sine of angle C over side length C, so sine of 50 degrees over 1. And we should set that equal to the sine of angle B over side length B, since we know that side length B, which is 2. From this, we can see that the sine of B is equal to 2 times the sine of 50 degrees. And this is approximately 1.53. At this point, this looks exactly like what we've seen in the past. However, if we try to solve for angle B by taking the inverse sine of 1.53, we're going to get an error on the calculator. And that's because this number, 1.53, is bigger than 1. So remember back when we defined sine of an angle, sine of an angle must always be somewhere between -1 and +1. You can think of this using the graph of the sine function, where the y values kind of alternate between -1 and 1, and the graph has a wave shape kind of bouncing back and forth. Or you could also think of the sine of an angle being the y-coordinate of the point on the unit circle. The unit circle, the largest y value is the point at the top, which is +1, and the smallest one would be the point at the bottom of the circle, which is -1. And so sine of B always has to be between 1 and -1. And if we get a value like here, where this number is bigger than 1, then this is an indication that there is no angle B that works with our given situation. And so if we ever get in a scenario like this where we have a sine of an angle being bigger than 1, the conclusion is that there is no triangle possible with this given information. The sides B and C are just simply too short to meet up at another angle.